Alrighty, folks, hello and welcome back. We are now on lesson number 7. This is going to wrap up module number 3. This should be about a lecture and a half to kind of get through this material. So what we're going to be talking about today is, again, a continuation of generalized linear models. So the last lesson we started with Poisson regression dealing with count data. This time around we are jumping to logistic regression. So kind of just a lead into this topic here. Imagine you're a marketer at an e-commerce company and you want to predict whether a customer will make a purchase. So we'll define making a purchase as a 1 and not making a purchase as a 0. So based on a couple of different factors, this could be things such as age, income, browsing history. So this is a binary classification problem where the response variable y is binary, so it only can accept two options. Either pass, fail, yes, no, 0, 1, that is it. So we're assigning a success or a pass as a 1, which in this case would represent a purchase, and a 0 for, say, no purchase or a failure. All right, so questions we may aim to solve. So 1, what is the likelihood that a customer will make a purchase on a given set of predictors? So again, for a specific age, income, and browsing history. A second question, well, how does each predictor, age, income, browser history, again, if these are the three that we are dealing with, influence the likelihood of making a purchase? So for question 1, let's think about this for a second. What are we looking to achieve actually in both of these? But specifically now for question 1, here we are looking to predict based on specific inputs for our predictors. Now as question 2, we're not asking to predict anything. Here we are looking at how those predictors influence the model in terms of the response. So the response, the outcome is either a pass or fail, yes or no, buy or don't buy. All right, so logistic regression is going to be the perfect model for us to be able to deal with such types of problems. All right, so decision versus volumes. So when we're talking about logistic versus Poisson, because we've just did the Poisson regression, so now we're going to contrast these two things. So with logistic regression, we're looking at things like, will they make a purchase? So that's the type of question that we are going to ask, a yes or no, simply binary. We can almost think of this as a first step. Then the second step is, well, once we do know, so if they are going to make a purchase, Poisson will tell us, well, then how many based upon, again, specific predictors. All right, so with logistic regression, it answers the decision question, will a consumer make a purchase, yes or no? And as I said for Poisson, this answers the volume question, given a purchase, how many items or visits? Now, what's going to help us with this is what's known as the odds ratio. We will talk about this in a few slides, so I'm not going to formally define this now. But the odds ratio from logistic regression gives insight on what influences the likelihood of the purchase. So this is our predictors and how we specifically look at the predictors and how they influence the response. So Poisson gives intensity once the event has actually happened. So again, in terms of the volume, how much volume once the outcome has actually happened. All right, so we've already seen models like Poisson that predicts counts, how many clicks, how many purchases, or how many support tickets we can expect. So logistic regression, speaking is not my strong point again, though it hasn't been for the entire term, so we'll just go with it for now. Logistic regression is asking a different sort of upstream question. Does the event happen at all? So in our e-commerce context, the first question is whether a visitor converts. And we're talking about converts as whether they make a purchase. So that's a decision problem. So if they do convert, Then we can think of a downstream. We might care about is the volume problem. So that's why I said we can think about this in terms of two parts. The first part is whether or not they will do something, and then how much of that something will they in fact do. So how many times, or how many items do they buy? How many times do they return? So on and so forth. So really, that's where the Poisson and the other count models come in. So these things can work in stages. So think of it as a two-stage kind of pipeline. Like first, the logistic regression gives the probability someone converts or someone makes a purchase. The coefficients there expressed as odd ratios. Again, we'll be talking about that in just a little bit more than a few minutes, but in a few slides there. This tells us whether features push someone over the threshold into buying. So we'll establish what that actually means. What is that threshold for buying? And then conditional are these conditional on conversion? Then conditional on conversion when we talk about the Poisson. The Poisson regression helps us estimate the intensity or the quantity. All right. Think of anything else I want to add to this? Well, actually, the last thing is really just the separation of power. Or this separation is powerful in business analytics because it basically lets us tailor interventions. We can use logistic to target customers who are, say, on the fence about converting or buying, and Poisson to optimize inventory or upsells for those who actually do. So again, using these in combination, very powerful. All right, so let's formalize a couple of things here. So what is generalized linear models, GLMs? We talked about this in the last time, but again, just as a quick refresher on this, there's the three main components of this. So GLMs is a framework for modeling a wide variety of response variables that we've already know. We've seen this in terms of count data. So it extends traditional linear regression by accommodating response variables that do not necessarily follow, I will get this right one of these days, follow a normal distribution such as binary count or continuous variables. But with continuous variables, we're talking about things that are non-normally distributed because, of course, traditional linear regression is specifically for things that are normally distributed. So as we said, it has three main components, the first one being that random component, that response. So this describes, in our case, the probability distribution of the response variable. So for logistic regression, this is binary, so yes or no. So this is going to follow a binomial distribution, or Bernoulli when we're talking about the number of trials being 1. Of course, it's going to have that systematic component. So it's going to have that linear combination of our predictors and how that is going to link up with our random component. We're also going to have that link function. That'll be on the next slide. But it will be a slightly different link function than what we had beforehand. So again, this is the linear combination of predictor variables, also known as the linear predictor. So again, that is our eta, which is equal to our beta naught plus our beta 1 x1 all the way up to beta p xp. So all of the x's, of course, are our predictors. The betas are our coefficients that we are looking to estimate based upon the data that we do in fact have. And of course, how we link everything together, this is the link function. So this is the function that connects the linear predictor eta to the expected value of the response variable y. So if we want to recall here just for a second, for a binomial distribution with the number of trials being 1, again, that's a Bernoulli, the expected value of the probability of successes is, well, the expected value of y, which is just the probability that y is equal to 1 for a given value of x. All right, so the link function ensures, in this case, because we're dealing with a probability, that it has to be in that appropriate range. We know a probability can be between 0 and 1, but it can't be less than 0, can't be greater than 1, can be 0, can be 1, but outside of that, it just can't possibly happen. And when I'm dealing with those linear predictors, if I have just a line, well, that can go outside of 0 and 1 very easily. So we need to be able to transform this linear predictor into something that's going to model a probability, and that's what we are going to be looking at. What is the probability of success? And when I was talking about a threshold, well, again, we're going to establish what is the probability that someone is going to make a purchase, but we need to establish a threshold saying that, okay, if it's above 50%, then we're going to assume that they are going to make that purchase. Now, we may want to adjust that. We may want to make it higher. We may want to make it lower, not a lawyer, lower, but that's going to be dealing with the context of the problem that we in fact have. which is a completely different course outside of the scope of what we're doing here. We're just looking to calculate the probability. All right, so the choice of link function depends on the distribution of the response variable. We've already seen this where we have the log of lambda, which is dealing with the Poisson. Here we're going to look at two different ones, but we're mainly going to be focusing on just one primarily because it's easier to be able to interpret, and we'll see why that is when we get to that point in time. So all this talk about link functions, why do we use a link function? Well, again, first and foremost, it's to transform the predictors. The link function allows us to transform the linear predictors into a form that is more appropriate for the type of data we are modeling. So if I'm just leaving eta as is, well, this works if we're dealing with a traditional linear regression because, again, the things are normally distributed and it just lines up perfectly there. But for example, here when we are dealing with probabilities, again, it can only be between 0 and 1. And if I'm doing a line of best fit, well, that line will go above 1 and will go below 0. So I'm going to have possible values in there that are going to be outside of the scope of what my response can take. That's not appropriate. Thus, we have to do this transformation. So for example, the logit link function, which we're going to be talking about, and that's going to be our primary focus in logistic regression, converts the linear combination of predictors into probability. So we're going to use the logistic function, which is basically just an S function, which is bounded in between 0 and 1. There's other things that we can use as we'll talk about very shortly, but that's going to be the main one, primarily for interpretability. There we go. All right, second reason why, flexibility. The link function provides flexibility in GLMs to handle different types of data, such as count data, binary outcomes, and continuous variables with skewed distributions. So again, we can have this general framework for things, and we just have to pick that appropriate link function to be able to map the linear combination of predictors to our response or whatever type of response we're dealing with. So by choosing the appropriate link function, we can adapt GLMs to model a variety of response variables. And interpretability. The choice of link function often impacts the interpretability of the model. For example, in logistic regression, the logit gives an easy to interpret odds ratio, and we'll talk about that just coming up in a second, which tells us how the odds of the outcome will change with each predictor. All right, so since I mentioned odds, let's talk about odds and let's talk about probability, just again to redefine this. Probability was already discussed in your first stats course. Odds might have come up. If not, we're going to bring them up now. So first and foremost, starting off with probability, because this is what we are familiar with. The probability of an event happening is the likelihood that it occurs, represented as a value between 0 and 1. So for the probability of success, if y is equal to 1 for a given value of x, again, that's what that represents there. So y is equal to 1 given the value of x that we have. X would be the different inputs that we are presenting to our model. This represents the probability that the event y is equal to 1, a customer making a purchase, occurs given the predictor variable x. So that is all of the outcomes here have to fall again between that 0 and 1. It can be 0, it can be 1, it can't be anything outside of that, but it can be everything also in between that. So that means that the probability is a proportion of occurrence of the event relative to the number of trials or observations. And we saw this back how we calculated the probability versus relative frequency, which is the probability of something happening. So y is equal to 1. So this is all the so the number of purchase will say over n, which is the number of times or the number of customers that we did this. All right. Now, what are the odds? The odds are slightly different. So the odds of an event occurring is the ratio. So again, we're dealing with a ratio of the probability of the event happening to the probability of the event not happening. So that's it. It's the odds of something happening versus it not, or the probability of it happening versus the probability that it doesn't happen. So it's calculated as this. So odds is simply just the probability that y is equal to 1 for a given value of x. So that's the probability of success. The probability of failure is 1 minus that. All right, so the odds tell us how likely the event relative to the event not occurring. So just a quick, simple example here. If the probability of success, again, we'll say of making a sale is 80%. So if we ran this experiment over and over and over again, 80% of the time we would be making a sale. What are the odds of this? So the odds are, well, again, the probability of success, which is the 80%, so that's in our numerator. Our denominator is the probability of failure, so that's 1 minus our success, so that's 1 minus 0.8, or 0.8 over 0.2, which gives us 4. So that is a 4 to 1 odds. So 4 successes to every loss. Now, as you're going to see, and we're not going to have to do this, but it's good to be able to understand what we are going to be doing, kind of like we were dealing with Poisson when we were dealing with log lambda. We're going to be involving the odds here. But at the end of the day, what we're looking to get back is a probability. So if I'm given the odds, can I convert the odds into a probability? Well, of course, I have this formula here, which takes probability and gives me my odds. I can reverse this and get my probability from my odds. And I simply do that by saying the odds of success, so y is equal to 1 for a given value of x, is just the ratio of the odds to not 1 minus the odds, but 1 plus the odds. So odds over 1 plus odds gives me the probability. So again, for this same example, working backwards this time, so we knew the odds were 4. Again, 4 to 1. Every 4 wins, we get 1 failure, or every 4 purchases, we get someone who doesn't purchase. So how this works out as a probability, we know we started it as an 80%. Do we get back to 80%? Well, let's see here. So the probability that y is equal to 1, so we make a purchase for a given value of x. The odds are 4 over 1 plus the odds, 1 plus 4, 4 over 5.8. So if we're given the odds, we can get the probability. If we're given the probability, we can get the odds. Perfect. So this shows that when the odds are 4 to 1, the probability of success is 0.8. All right, so let's talk about some of our basic models here. We'll start with things that just do not work, and for the exact same reason why we said they just do not work. And then we'll get into basically what we are in fact going to be using. So you can kind of fast forward through this, but stick around if you're interested in seeing, again, why. All right, so we're going to start off with the first one that we're not going to be using, which is the linear probability model, or LPM for short. So the linear probability model tries to use linear regression to predict binomial outcomes. So if we write it as follows, and let's suppose we only had one predictor variable, then we're going to say y, or y hat, is equal to, well, the expected value of y, which is the probability that y is equal to 1 for a given value of x, which is just going to be beta naught plus beta 1x. So all we're saying at this point in time is I'm not going to link this in any special sort of way. This is just going to be exactly the same that we did with linear regression as we originally started in our Stats 1 course. So the link function is the identity function. All right, so however, the linear model is inappropriate for binary data because, well, there's a couple of reasons for this. The first one is it can predict values outside of the valid probability range of 0 and 1. Again, if I have my graph here, I'm going to have some line and say this is values between, or my outcomes between 0, this is my outcomes between 1. Well, I have specific values of x over here and over here that gives me things that are going to be outside of that range. So again, that's not going to be good. For specific values of x, we always want it to be between 0 and 1. This is why we're going to use eventually that logistic function, which is just going to be an s sort of function inside of there. All right, so it assumes constant variance, which is violated by the nature of the binary data that we do in fact have. So let's talk about that very briefly here. Well, actually, before we do that, let's do a little bit of visualization here. Let's jump over to R. Oops, I got a lot of stuff going on here. Let's clean up my area. Clean this up, yes. Let's clean this up, yes. There we go. So what we're going to do now is just create some synthetic data. And I'm going to look at the different link functions and kind of how we visualize these. All right, so I'm going to generate some random data. So I'm going to set the seed. The seed's going to be to 42. I'm going to generate 100 data points. So n is equal to 100. These are going to be a sequence between -3 and 3. So those are the possible x values that it could take. So I'm asking for 100 chunks in between -3 and 3. So I'm putting that in a vector x. Now I'm going to build their true probabilities for the logistic function. I'm not going to go into too much detail about this because we're going to be talking about this in the next little bit. But basically I'm using the logistic function to be able to calculate their true probabilities. All right, so now what I'm going to do is I'm going to generate some binomial data here. So some zeros or some ones, based upon, again, those probabilities that were just created. So I'm storing that in my vector y. So my vector x is between -3 and +3 with 100 observations in there. I've generated some probabilities based upon these values following a very specific logistic regression curve, or a very specific logistic curve. And then based upon that curve, I've established a vector y, which is also size 100, that brings things into 0, 1 context. Okay, so I have my x and y's. Before I plot anything, I'm going to build 3 models. The first model I'm going to build is my linear model. So I'm just using the simple LM function and say y is explained by x. Now I'm going to build my logit model. And we haven't talked about specifically the link functions, but we'll get to that. Again, I just want to be able to show you. So this is going to be the one where I'm using that logistic function to be able to map this. So here, I'm using the GLM function, saying y is explained by x, and the family that I'm using is, again, binomial this time. So last time it was Poisson, this time it's binomial. And there's also another link function. So this is the probit model. We won't really be using that, but it's good to be able to talk about. So here I'm just specifying the link that I want to be able to use. So by default, it's always going to be the logit. Here I'm saying I want it to be the probit. All right, so let's graph everything now. So let's pretend, again, that we just went out and we collected the data. And the data looks something like this. We have success or failures. We have people who made a purchase, people who didn't make the purchase, and it was based upon this sort of distribution. So I have everything either landing on a 0, or I have everything landing on a 1, and again, my values are in between -3 and +3. So here, if I tried to do a line of best fit to model this data, well, what would that look like? It would look exactly like this. So we can see for 3 or -3, +3, it's within that 0, 1 range. But what happens outside of there? Well, we're now dealing with values that are going to be less than 0. We're dealing with values that are going to be greater than 1. Well, that doesn't fit, because regardless of what x we put in, has to spit out a value that's going to be a probability, so it has to be between 0 and 1. And also, if we're looking to try and do a line of best fit, well, this isn't really hitting the data reasonably well at all. So in terms of being able to model what's happening here, this doesn't seem like it's doing that great of a job. All right, so let's see what the logistic function will do. Again, this is the S-shaped function. So here, that's the red line. It bounds everything between 0 and 1. So it collects a little bit at the top, collects a little bit at the bottom, and it transitions downwards. Now, just notice the steepness of that transition. So if we do the probit model now, in this case, very, very similar. It's the green line, which almost covers the red line perfectly. Slight differences here. More aggressive at the top and at the bottom, and kind of a longer, not as steep in terms of the transition between 0 and 1. So in this middle part here. Now, these two, by the look of it, it may seem like it doesn't matter which one we choose, but in terms of being able to interpret things, it is going to matter for us. And this is why typically we use the logit function. Now, we can use the probit function if we know something about the underlying nature of the problem that we have, and we'll talk about that in a second. But for the most part, again, for what we're going to be doing, we're going to be using the logit link function. All right. So let's talk about now that constant variance. That was the second part to this. Let's jump over to switching this things up. Let's look at my slides for this one here. All right, so first and foremost, let's talk about how we calculate the variance for binary random variables. So to calculate the variance, we use the variance formula of random variables. Now, you probably saw this back in your Stats 1 course, and if you've forgotten it, not a problem. Here it is again. So the variance is simply just, well, what is the expected value of y squared minus the expected value of y all squared? Now, here's the simplification that we have. So for binary random variables, we know that y, so again, what y can take is only going to be values 0 and 1. That's it. That's all. So therefore, well, what's y squared? Well, what's 0 squared? That's still 0. What's 1 squared? That's still 1. Nothing changes there. So in this case, the expected value of y squared is exactly the same thing as the expected value of y. So we can actually rewrite this. We can write it as follows. The variance of y is now not y squared, but just e of y minus e of y all squared. Well, we can do a little bit of factoring here. So what do we get? Well, we get the expected value of y times 1 minus the expected value of y. And as we defined beforehand, the expected value of y, this is the probability that y is equal to 1 for a given value of x. So if I do that substitution in, well, e of y, this is again the probability that y is equal to 1 for a given value of x. 1 minus the probability, well, that's, if this is the probability of success, this is the probability of failure. All right. So in linear regression, we assume that the variance of the errors, the residuals, is constant across all levels of the predictor. So for the constant variance, this is something that we definitely need. But in logistic regression, because the variance of y depends on these probabilities. So if the probabilities change, the probability of success changes, going to change the probability of failure, which means we're not going to have constant variance across all of these things. So the variance is not constant and varies with the predicted probabilities. So this is known as, well, we have homoscedasticity. I'd never say that one correctly. And the hetero version of that. There we go. I'm not even going to bother because I butcher that every single time. It's even worse than when I try and say these in class. All right. So when we have probabilities that are really close to 0 or really close to 1, then that variance, there's not a lot of change in that variance overall. It's relatively small. So we don't have issues in that regards. But what happens when we get probabilities closer to 0.5? Well, things around 0.5 provide a much larger variance, and this is where things really start to become a problem for this constant variance assumption that we need. All right, so since the variance of y is not constant across all levels of x, this violates our assumption under the linear regression. All right, 1 second here. Don't need that just yet. Perfect. Let's bring this back up. All right, so let's talk about the link function now. We'll look at the logit link function, then we'll look at the probit one. We'll talk about compare the two, and then we're going to start building from there. All right, so the goal in logistic regression is to model the probability of y is equal to 1 for a given value of x. So this is, of course, the probability of success. So how we're going to do that to begin with is using that log or logit link function. So in the logistic function transforms the linear combination of predictors, again eta, into probabilities between 0 and 1. All right, so how do we do this calculation? Well, this is the formula for the logistic function here. I'm never going to ask you to memorize this, so don't bother trying to memorize this, but this is just e to something over 1 plus e to something. That just something happens to be eta, the linear combination of our predictors. So if actually you remember when we were talking about, or when I was doing the graphing of these examples here, and I said, this is how we create these probabilities, blah, blah, blah. It's all based upon this function here. All right. But this is ideally what we want, but on the right-hand side, this is not what I want. So at the end of the day, again, I want to be able to link what I'm looking for, or a transformation of what I'm looking for, to my linear combination of predictors, not this e to my linear combination of predictors all over 1 plus e to my linear combination of predictors. I don't want that. I just want that linear combination. So I need to do a little bit of mathematical rearrangement here. I'm not going to go through all the steps. You're more than welcome to try this. It's not that difficult to do, but I'm never going to ask you to do it. So if we rearrange what I have circled up top here, and again, what I'm looking for is on my right-hand side, I just want my beta naught plus my beta 1x all the way up to my beta p xp. What I do, if I can rearrange this, what I'm left with is on my right-hand side is e to that. Okay, I can fix that. What's on my left-hand side is the probability of y is equal to 1 for a given value of x divided by 1 minus the probability of y is equal to 1 for a given value of x. This is, hopefully we remember, this is the odds. So the odds is equal to e to the beta naught plus beta 1 x1 plus all the way up to beta p xp. There we go. But again, what I want on my right-hand side is not e to this. I just want my betas. So to get rid of the e, again, this is where I use the ln function, or log function, natural log function. So taking the log of both sides, I get the log of the odds, or log odds, which we simply just define as logit for p of y is equal to 1 for a given value of x, and this is equal to our linear combination of our predictors. This, again, is our eta. All right, so this is our link function. We're not linking directly the probability, we're linking the odds of success. And this is why I said in that previous couple of slides, if we know what the odds are, we can calculate the probability. If we know what the probability is, we can calculate the odds going back and forth. So here we're calculating the log odds, but we can always find the odds based upon that and then find the probability based upon that. So the logit link function is the log odds of the probability of the event occurring, which we define as exactly this. So I have the log odds is equal to beta naught plus beta 1x all the way up to beta p xp. All right. Now interpreting the coefficients. This is the key part here. So the coefficients beta 1, beta 2, all the way up to beta p represent the change in the log odds. So this is the key part here. It's not change in the odds, it's the change in the log odds of the event occurring for 1 unit change in the corresponding predictors. Same as before when we're dealing with Poisson, this becomes a pain to be able to try and to interpret. So if I increase one of these values of x by 1, what changes? Well, its respective beta. Well, what does that mean? Well, that's just the log of the odds changing. Okay. let's just talk about odds, not log odds. Let's get rid of that. Well, we're going to do exactly the same thing that we did in the Poisson, which is just taking e to both sides. So if I look at e to the beta j, this is going to give me the odds ratio for that specific predictor. So this is going to represent the multiplicative change in the odds of success for 1 unit increase in x sub j. Of course, holding all other predictors constant. So since it's a multiplicative change, if that value e to the beta j is greater than 1, we're going to see a multiplicative increase. If e to the beta j is less than 1, we're going to see a multiplicative decrease. And if it's equal to 1, well, we see absolutely no change. One last thing to talk about before I run away on this. All right, so just a couple of mathematical characteristics of this. So the logit model produces probabilities bounded between 0 and 1 because the logistic function squishes the output of the linear predictors into this range. So the logistic function is S-shaped, meaning that small changes in the predictor have significant impact on the probability when the probability is near 0.5. So there's a lot of variability that we said already when we get to those probabilities around 0.5. But of course have diminishing effects because of that S shape. So there's very little change on the outside of the tails. But that middle part where we transition from 0 to 1 or 1 to 0, however you want to go, that's where a lot of the variation is going to happen inside of here. All right, so let's talk about the Probit model. And again, we're not going to be using this, but it is something that is good to know. And because it looks very, very similar when we did the graph, which you can still see the graph right. Oh, perfect. I did point right to it. The graph right there, our red and green lines basically overlap one another. So you would think that they're almost identical, but there is slight differences between the two. All right, so the Probit model is another model for binary outcomes that uses the Probit link function. So instead of the log odds transformation, the Probit model uses the cumulative distribution function CDF of the standard normal distribution. So what this means is the probability that y is equal to 1 for a given value of x, this is equal to phi, where phi is the CDF of the standard normal distribution with the input beta naught, beta 1, x1, all the way up to beta p, xp. Okay. So this function transforms the linear combination of predictors into values between 0 and 1. So the transformation I need to do here is I just need to undo phi, which is taking phi inverse. So phi inverse on the probability of y is equal to 1 for a given value of x is equal now to our linear combination of predictors. So the same things as we had beforehand, but what we had beforehand, it was some function. Input of that is the odds. Here we have some function. The input of that is specifically our probability. So that makes it a little bit nicer, but the interpretation of all of this becomes a little bit more difficult. So the inverse of the CDF, that's phi inverse, is used to model the linear predictors, just as the logit function is used in the logit model. All right, so interpretation of the coefficients. This is where things become a little bit more problematic. So the coefficients beta 1, beta 2, beta p, or all the way up to beta p, in the Probit model represent the change in the Probit inverse CDF of the probabilities. That's even more annoying to try and be able to interpret there. Of the event occurring for 1 unit change in the corresponding predictors, again, leaving everything else fixed. So unlike the logit model, the coefficients in the Probit model do not directly translate into odds relations, making them less intuitive to interpret. So to get the odds ratio for a predictor, you would need to exponentiate the coefficients, but it does not have the same clear-cut interpretation as the logit model does. Because at least when I was taking e to whatever that beta was, well, that function that does my transformation, that was my ln. So ln and e undo one another, so what I'm left with is just the input of that, which is, or the input that I had inside of my ln, which just happened to be the odds. So those things canceled each other out. So here, if I was talking about it in that sort of regards, this would be e to the phi inverse of my probability of y is equal to 1 for a given value of x is equal to e to some beta j. Yeah, that's a lot less intuitive there. So for us, we're going to be sticking with the logit model. So in this case, again, same idea, the mathematical characteristics. The probit model uses a normal distribution. So it's based upon the assumption that the underlying latent variable is normally distributed. Okay, what exactly does that mean there? Do I have a way of being able to... Do I have a next slide? I might have a next slide. Oh, actually, what I could do here is I think I can do this. Screen. White screen. I think I can write something on here. Perfect. This will be a little bit more better in that regards. All right. So what do I mean by this underlying latent variable here? Well, let's suppose we're trying to predict whether a loan application is approved. So we'll say approved. We'll give this a 1, and denied is going to be a 0. All right, so again, all we're being able to see is the 0 and 1, whether or not you're approved or you're not approved. But typically when these things are happening, you're going to a bank, there is a part that's not observed. So there is sort of like, we'll say, a credit worthiness. A credit worthiness score that the bank would use. And we'll say this is some hidden number, and we'll call this hidden number Z. So this score is going to be continuous, so it could have values, say 1.2, 3.7, so on and so forth. And the bank uses this and approves the loan based upon this score for some given threshold. So for them, this Z is equal to some beta naught plus beta 1, x1 all the way up to beta p xp plus our epsilon, where this is going to be epsilon is normally distributed, we'll say between 0 and 1. So a mean of 0 and a standard deviation of 1 is what I mean by that. So what we observe y is equal to, well, there's two possible outcomes, 1 and 0. And let's suppose we get a 1 if z is greater than 0, and if z is less than or equal to 0. We get a 0. So what does this actually mean? So this means that the probability of y is equal to 1. This is equal to, well, really, the probability of the underlying variable here. So this is z greater than 0, because I'm asking what is the probability of success? That's my y is equal to 1. When do we get a 1? Well, we get that when z is greater than 0. So this is the probability that, well, z I can just simply rewrite as beta naught plus beta 1 x1 all the way up to beta p xp, and this has to be, or sorry, plus epsilon, which has to be greater than 0. Which this is just, since it's normally distributed, this is phi of beta naught plus beta 1 x1 plus all the way up to beta p xp. Again, where phi, I'll just state this here, is the standard normal CDF function. So that is the probit link. Okay. So that's what we're talking about. There's some underlying nature of this, which is not just 0 and 1, because that's what we observe, and that's perfectly fine if that's the only thing that's there. Then we have the log odds function to be able to do this. But if we know that there is in fact this underlying a latent variable, in this case z, which is in fact normally distributed, then this is the technically more appropriate model to use in that regards. Yeah, so it's a little bit more of a long-winded explanation, but that's it there. All right, so that's the first bit. So the underlying latent variable is normally distributed in this case. If we're talking about loan applications being approved or denied, this is, say, that credit worthiness score. Okay. The normal CDF is S-shaped and has similar behavior to the logistic function. So I'm back to the mathematical characteristics here. But it's steeper at the center, so around that 0.5, and flattens more quickly at the extremes 0 and 1. In the Probit model, the predicted probabilities are more conservative near the tails, so they're closer to 0 and closer to 1. Just because we have that, everything kind of quickly flattens out towards the extremes. All right, let me switch back my screens here. That's not the one I wanted. There we go. All right, how are we doing for time? We're almost there, actually. So now this will be broken up into 2 lectures. That's perfectly fine. All right, so when to use the logit versus Probit model. So for the logit, we use this for interpretability. So this is going to be a big one because the numbers, the calculations, these just make it easier to be able to understand and interpret. So the logit model is often preferred when you want a clear interpretation of the coefficients in terms of the odds ratio. This is especially useful in applications where understanding the multiplicative effect of each predictor on the odds of the event is important. So this can fall into marketing or, for example, medical studies. There's a simplicity to it. The logistic regression model is easier to interpret because of the straightforward relationship between the log odds and the predictor. That's it, that's all. So that linear combination of predictors, we have the log odds. These two things are equal to one another. Awesome. I can take e to both sides and I get my odds ratio, and I have just the odds. All right, what about the Probit model? Again, the theoretical considerations. If that latent variable, again, is assumed to be normally distributed, then this is the way it should be going. Comparison with the logit. So while both models are often used interchangeably in practice, the Probit model may be preferred when modeling certain types of data that naturally fit the assumptions of normality, or when a more conservative approach to predicting the extremes is needed. So when we're talking about it flattening out a lot quicker in those tails, that sometimes is in fact preferred. There's a financial and economical applications of this. So in some fields like economics and finance, the Probit model is preferred because it has a direct connection with the normal distribution of the errors. All right. So that's everything that we need in terms of the link function. We have the 2 different ones. You've kind of seen the 2. What we're going to be focusing on is the logit link function, but you know both of them are out there now. All right, so let's go into the actual building of the model. So the first thing that we need to look at is the assumptions of the model. So same as beforehand, we were dealing with the simple linear or the multilinear or the traditional linear that we were dealing with back in Stats 1 or the Poisson. We all have assumptions that we are making on this one. So 4 main assumptions. First is the binary response, or response variable has to only take 0s and 1s. Of course, we have the independence of the observation, same as before. The variance structure. Now, if we are talking about in generality, and the number of trials doesn't have to be 1, typically, depending on the context of things, we do keep this as a 1, at least for the examples that we're going to be playing around with, but it doesn't necessarily have to be. So the variance is the number of trials to the probability of success to the probability of failure. So if we're talking about just a single trial, going out and getting one person a yes or no based upon that, then this is it, n is equal to 1. And again, as we mentioned, the variability is highest when the probability is close to 0.5. All right, linearity, making sure that link function makes sense. So if I were to do a scatter plot of things, if I transform my linear predictors and my log odds of things happening, then what I should see is a lineup or being able to do a lineup best fit. All right. So in terms of estimating the parameters, I'm not going to get into too much detail about this. This is going to be a quick kind of hand-wavy sort of explanation of this because I think it is in fact good to know because you would have seen how to be able to get the estimates when you're talking about linear regression from back in your Stat 2601 course. Here, how we do it is not as easy to be able to do. So let's talk about how we actually come up with the estimates for our parameters. So for our beta naught all the way up to beta p. All right, so with other models, our goal is to find estimates b naught all the way up to bp, or bk in this case, for my beta naught all the way up to beta k. Logistic regression uses maximum likelihood for parameter estimation. So consider n data points, and we'll label those data points we'll label the with labels either 0 or 1. So I have 10 data points, and those data points can be 0 or 1. That's it, binary. So let's take those 10 data points, or those n data points, we're going to break them up into two different groups. So this is going to be one group, this is going to be the other group. So this will be my 0 group, this will be my 1 group. All right, so the first part, for data labeled 1, so that's everything that's inside of here, this would represent all the data points that are successes, because 1s would represent a success, 0s would represent a failure. So S and F, successes, failures. All right, so we want to find estimates such that the probability of X hat, so again, we want to be able to build a model that gets us a probability for the given values of X, so whatever we take from in here should get us as close to 1 as possible. So if I'm building a model that's going to represent that data inside of there for some given values of X, I want to make sure that I have coefficients that when I plug those values of X in, I'm going to get values that are going to be really, really close to Y because I know that they all represent successes. And same idea here, I want a probability function that when I put in my X's for my data here, that 1 minus the probability is going to get me really, really close to 1 because this should all represent zeros. This should all represent 1s. So if this all represents 0, then 1 minus 0 should get me close to 1. So the end idea is I want to build a probability that's going to spit out something that's going to be close to 1. And it's either I'm going to take it as is when I'm dealing with a success or 1 minus as is when I'm talking about a failure. All right, so since each data point is independent by assumption, then the likelihood that they all happen is the product of each probability. So what I mean there is, if we remember back from our Stats 1 course, if we had two events, so I had event A and event B, and we'll say the probability of A is equal to 0.4 and the probability of B is equal to 0.8. Oops. Now we ask the question, what's the probability of A and B, them happening at exactly the same time? So the probability of A and B, well, this falls into conditional probability unless we know one thing. And that one thing is, are these events independent? And if they are in fact independent, then this is just equal to the probability of A times the probability of B. So 0.4 times 0.8. And there we go. Simple as that. Multiplying the probabilities through. So if they are independent, the probability that the first happens and the second happens is just the probability of the first times the probability of the second. So in our case here, if we expand this idea to n data points, and each one of these n data points are independent, well, what's the probability that all of them happen at exactly the same time? Well, that would be the probability of the first times the probability of the second times the probability of the third. So probability of the first, probability of the second, all the way up to the probability of the nth. Now what I want to do is I want to be able to build a formula for this. So if I'm talking about all of my successes, everything that's labeled 1, that stream of products is just what I have here. So I'm saying for all successes, where my y is equal to 1, I'm just multiplying those probabilities together. When I'm talking about failures, that group of all failures, all of their probabilities, well, that's 1 minus the probability. I'm multiplying all of those together. And now if I merge these two groups into one, and I still wanted to be able to calculate this, this is my likelihood function given this specific beta, which is the product of the two. Now I'm not taking the two at the same time because it's going to depend on my y. So for each value of y, remember it's either going to be a success or it's going to be a failure. So this is either going to be a 0 or 1. This is either going to be a 0 or 1. So if the first one is 0, well this whole factor disappears. And if this is a 0, well this just leaves me with a 1, so I just left with 1 minus the probability. Where on the other hand, if my y was equal to 1, this factor wouldn't disappear, but this one would disappear. So again, if I look at all n, they're all showing up there. All right, so this is what I want to be able to solve for. What I want to be able to solve for is I want to be able to find some specific beta, so some parameters, such that I get the largest likelihood. So I get the largest possible outcome for success based upon all of my probabilities happening. So what's the probability that I get the first one right, and the second one right, and the third one right, and the fourth one right? I want to be able to find that b to be able that allows me to do that. Now solving this equation becomes incredibly difficult because, well, first and foremost, it's a product. So I can cheat a little bit and turn this into a summation. Then we have techniques for being able to solve those afterwards. But again, doing that, I have to take the log of both sides. Doing that, basically I work down into what I have here, rearranging things I'm getting here. Again, I'm not going to go through all of this in line by line detail, but basically what we're doing is I'm building something that is going to look exactly like this at the end of the day. And this is what I'm looking to solve for. Now, this does not have a nice closed form solution to it, such as the other problem, so there's no real formula for being able to do that. But we do have approximation algorithms such as the Newton-Raphson method to be able to approximate what a solution for this is in fact going to be. So by solution, I mean we are going to try and find a beta naught, beta 1, beta naught, beta 1, such that again we get the maximum outcome of this. And the maximum outcome of this reflects what happens when we get the probability of the first right, the probability of the second right, so on and so forth, all the way up to the probability that we get the nth one right. There we go. I think for now we'll introduce this example here. And then we'll start playing around with this next class. So this was a good lead into everything. This was a little bit longer than I was expecting it to be. I apologize for that, but we did need some background information and why we're doing all of these things. So this is the example that we're going to be playing around with for the rest of the next lecture here. There we go, which will be up right after this one. Okay. So for exercise 1, you are a marketing analyst with an e-commerce company. Your goal is to understand and predict whether a visitor will convert, so make a purchase, based on their behavior and source. So the data that is evaluated, will be simulating this data, but the data that is evaluated to us is, the first is going to be time on site. So how long were you there? This is going to be recorded in minutes. Prior visits, is this the first time you're here, second time you're here, 100th time you're here? How did you connect to this? Was this done through a mobile app, or is it done through a desktop? How did you hear about this? Was it through an email, ad, referral? And at the end of the day, were you converted? Did you make the purchase? So 1, 0 otherwise. So that's the data that we're going to be doing. So we're going to be given this, and we're going to be asked to build a model, interpret that model, modify that model exactly like we did beforehand. And that's going to be in the next lesson. So we'll see you back then. If you have any questions, comments, concerns, feel free to reach out. Otherwise, yeah, we're almost done. Module number 3, and then just time series left. Excellent. Until the next time.